My name is Paul, and I am working in the SRE team in Dublin. And today I will present a talk about the Linux telephony, something completely unrelated to it. But anyway, so I already gave the presentation of this kind on this year at our Linux symposium. And how I want this presentation to be different from the OLS is I have a significant introduction, large enough introduction for the people who are completely new to the telephony. If you feel that the introduction is overly detailed or overlong, or if you have any questions, you feel free to interrupt me in the course of my presentation. So let's go. This is the approximate outline of my presentation. So I will start with the introduction of two generations of telephony, which is the traditional telephony and what's called voice IP, packet switched telephony. I will mention how to implement voice services on the Linux and using the commodity hardware. And I will briefly talk about the current state of the Linux telephony in general. So, for the introduction, as I mentioned, I will distinguish two kinds of telephony services. But they are both telephony. So they have in common a couple of basic things. The one of those is that in telephony we always have a conversation, which is the bidirectional media transfer, either voice or if you go to the more modern installations, it can be video conferencing. Then when you set up the conversation, you need the basic ways to control this. So you need the ways to do a call setup or call tear down, and so-called advanced functions, which is the call forwarding, call transfer, and multi-party. They are called advanced, but they are now common to the old telephony. So I start with the traditional telephony because this is the telephony that everybody used right now. So the traditional telephony is what we call the public stationary telephone network. And this is basically what the public stationary telephone network is the same as the internet for all those interconnected networks. So this is the network of telephones addressable by their phone numbers, which you can dial. And the PSTN right now includes not only the stationary phones, which is the plain old telephone system like wires, but also mobile phones, the thing that usually called public land mobile network. And the customers to this network are usually, customers are analog customers, and they're usually connected by analog type lines in the plain old telephone system. But if you have a cell phone, the digital analog conversion is in your phone, but you still analog customer. Voice in PSTN networks in general are circuit switched. So, which means that at the call setup phase, you establish a circuit from one subscriber to other party, and the customer and the circuit between them consist of multiple circuits of many types. For example, two analog circuits from you to your exchange and from exchange of another party to another party. And digital circuits, which is called the digital signal 1 circuit, also called a bureau channel in ISDN. It's the basic digital circuit of the voice in the PSTN. So this is approximately how it does when you call. And because it is circuit switched, the circuit is seized for all time of your discussion. So you basically just reserve this bandwidth for you. And so while I talked about the digital circuits, and I mentioned that we also established the circuits between the exchanges in the middle of the conversation. Usually the exchanges are connected together by trunk lines, which consist of multiple circuits, multiple individual circuits. And this is usually E1 or T1 lines. E1 is Europe and T1 is America. And the basic characteristics are on the slide, basically of these lines. And when someone talks about signaling protocols and signaling in PSTN, this is the call control and management protocols, which is used to do the call setup or tear down or various functions or call routing and control the state of the PSTN network itself. So there are various signaling types which I mentioned on the slide. I will make the slides available, but I will talk about a couple of them. For example, the subscriber versus trunk signaling is the subscriber signaling is used on your subscriber line. For example, if you use the analog phone, then signaling protocol on your analog line is the DTMF signaling, the beeps that your phone produces when you dial the numbers. And the trunk signaling is performed on the trunks, and there are different kind of trunk protocols which I mentioned, which I will mention on the next slide. So I don't know if you can see this. I prepared it for the Linux symposium. So basically the two signaling protocols I want to mention in details is the signaling system 7 and ISDN Q931. The signaling system 7 is the de facto standard of interconnecting all exchanges in the world. So all phone exchanges, large and small, are using the SS7 to talk to each other. And this protocol is out of band, which means that signaling transferred via different circuits than data. This is one of the properties of signaling protocol, which was mentioned on the previous slide. And this is genuinely good because a bit of history lesson. 20 years ago, probably, there were a different signaling system as a standard signaling system 5, which was in-band. And if you have an in-band signaling, then you basically can forge the signals of the signaling protocol and do what's called freaking at the time. So anyway, and the SS7 is not a single protocol, but a protocol stack, which is can be represented by the same model as the usual network stack, and is extensible. So, for example, when mobile networks were introduced, we were in need of new protocols to control the state of mobile network and the state of the customers, like the subscriber registration and the so-called authentication and HLR interrogation and short messages, SMS messages. All of those are implemented in the protocols called transaction control application protocol and mobile application part. So basically, there are extensions which run transparently on the old network infrastructure. The ISDN Q931 is another signaling protocol, but it is used mostly between the PBXs, private branch exchanges, and the carrier exchanges. It is much easier to set up. It doesn't require the complex routing setup of SS7. But it has some limitations in the design. For example, in SS7 we can, as I said, because it's out-of-band signaling, we run the signaling over different circuits, and in SS7 we can basically run it totally different ways. So voice data run over the lines which are latency sensitive, and the signaling run over the other lines which are not so fast, and latency is not so good, but they are more reliable in terms of packet loss or data loss. So in Q931 it is much simplified because it was basically intentional. You usually use single E1 or single T1 line to connect the PBX to carrier. But anyway, it's the digital, it's a modern signaling protocol which is used right now. And there are a couple of other obsolete and deprecated signaling protocols which are mentioned on the bottom line of this slide, but they're usually deprecated, but they are still used in some old installations. By the way, you can find the complete analog systems in old installations, but this is the different story. Anyway, so as much about the signaling protocols. And right now, I'll talk a short introduction to packet switched telephony to voice IP. When someone talks about voice IP, usually means the services and the protocols and the technologies to route calls over the IP network. So, by the way how IP network works, what we get from the voice IP is the packet switched telephony, which means because the underlying network are packet switched, but we still need the bidirectional conversation. We still need to talk to other party. So we built a virtual circuit over the packet network. The problems here are because in PSTN, when we build the circuit, it stays the same all over the time of the conversation. And we have the same bandwidth and the same latency. Here, we run over the network which can change in every time and which have its own weather in the terms of bandwidth and latency. So this is the difference which caused by the packet versus circuit switched. And there are protocols which are so-called voice IP protocols, which are kind of used to do this. And there are various types of protocols. I will mention the most widespread. The most widespread is the SIP, Session Initiation Protocol, and H323. Those are signaling protocols, because as in traditional telephony, we have two types of data which passed between the nodes in our network. We have a media, the audio data or a video, which needs to be passed to other party and with obvious latency requirements. And we have a signaling which used to control this. So the SIP and H323 are signaling protocols, and they basically used to describe the endpoints to each other or to central server which will route the call. And when all the session setup in CPOR 323 is completed, then RTP, so-called real-time protocol, which is some protocol over the UDP, is used to transfer data. And preferably, it is used to transfer data between the endpoints. Even if we had intermediate routing for our signaling, we need to transfer data between the endpoints to minimize the latency and in general to minimize the load on the routers. There are also IEX, inter-exchange protocol, which was invented by the authors of one of the open source software packages **. I will talk about later. In IEX, both signaling and media are transferred in a single stream. And these have advantages and disadvantages. Advantage is that we can easily penetrate the net. And disadvantage is that, as I said, we need, in CPOR 323 case, we can route the media directly between endpoints. Here we need to pass the media through our server, which will process it. There are also other protocols such as SCCP or MGCP. Usually they are used for some. They are not generic like CPOR 323. For example, MGCP is Media Gateway Control Protocol, which is used to control media gateways, basically. Or SCCP is the proprietary Cisco protocols, which is used only in Cisco IP phones. And some of those protocols require server to operate, and some aren't required. So much about the signaling and how it works in general, but we still need to pass audio data between our endpoints. So after the call setup is done and for example, we choose the RTP to transfer the media, but we need to encode your voice and pass to other party, and another party will decode. And this is the part which is handled by voice codec. And there are plenty of voice codecs out there. The problem is that the most popular good codecs like G729 is patented. And other codecs, there are some free codecs, for example, Speaks, which is very good, but it isn't used in consumer equipment. So when you're trying to create some network using some equipment which designed for voice IP, you will need to deal with this. And not all of those codecs are invented for voice IP. For example, G711 is the PSTN codec. So as I mentioned, you use the digital DS0 to transfer voice in PSTN, and the voice is encoded using G711. And in your cell phones, you use GSM 610 codec. So any questions about introduction? If you have, please ask. I may skip the part, but anyway. No questions. So let's talk about the implementing voice IP. So in voice IP network, we will have basically two types of nodes. The first type is the endpoint. So endpoint is what generates the audio data, the voice payload actually, and it talks some voice IP protocol. So it can connect either to the voice IP server or to some voice IP endpoint and pass the payload in two directions. So one example of the endpoint is the soft phone. Another example of the endpoint is some voice IP hard phone, which is plugged to Ethernet. And the other type of the node is the soft switch. And the soft switch is, or a voice IP server, is why it's called soft switch, because it functions like a switch in a traditional network. So it can do, for example, the endpoint registration. It can do a call switching, actual call switching, which means between two endpoints if one calls other. It will do all call setup, and all media transfer will be handled by this. And it can do some advanced functions, which I mentioned as advanced in the introduction slide, like multi-party conversation, some call forwarding or whatever. And because it is soft switch, it is basically, it's a software. We can do almost anything here. So especially if we take some open source software to do this, we can extend it as we want, and modern open source voice IP packages can basically use any scripting language to extend themselves. And you can, for example, write an IVR, interactive voice response, or some auto-responding system, or can take open source speech recognition software and do something with this. So the two special cases of the voice IP services is the multi-protocol soft switches and signaling proxies, and the soft switches with the PSTN interface. So the latter is basically the gateway, which is integrated with the soft switch. So
is it necessary to have the soft switch, or could you just call directly?
You can, if your protocol, okay. The question was, is it necessary to have a soft switch, or you can call it directly? There are protocols which require server to operate. And in this case, you will need a soft switch. But if your protocol allows you to call directly, then you can do this directly. For example, H323 can call directly between endpoints, also with SIP, and it's just so the former is multi-protocol soft switches and the signaling proxies. The one particular example of this kind, as I said, both SIP and H323 uses the same protocol to transfer the payload, the RTP, which means that if you write some code called signaling proxy, you can integrate SIP and H323 network. So you can have a bunch of devices which talk H323, a bunch of devices which talk SIP, and they will talk to this server, but media will be passed directly between them, because the server will expose the IP addresses of other party to each other, and everything will work. So there are a couple of examples of the voice IP software. As I said about the endpoints, we have a clients which are endpoints, and there are dedicated hardware clients or soft phones. I mentioned a couple of soft phones, of open source soft phones for protocols which I also mentioned, so SIP, H323, and the AIX. I also mentioned Skype. I should mention a Google Talk here. Anyway. And they're also soft phones because they allow the conversation, but anyway, the Skype uses some proprietary protocol, and the Google Talk uses some open protocol, which we can hardly find implemented anywhere. So the servers, the most famous and most widespread server package is the Asterisk. And it's the open source, of course, and if you install it, if you want to play with it, you can install it, and you will get out of the box SIP, IX, and working IVR. So you can use any SIP soft phone and call your freshly installed Asterisk and basically play with the telephony, and it will work okay. And this is the result of more than, I think, more than 4 or 5 years of development. Anyway, there are other software packages out there. For example, Gate. It's the completely different architecture from Asterisk. It started a couple of years later. And the architecture is much cleaner. You can look at it if you want. Also, it is less feature complete than Asterisk. Asterisk has a lot of convenience functions called applications. And in E8, it's just a basic engine. It's very fast, but it's basic. If you want to extend it, you need to write a lot of code. And there are also packages which I mentioned in the bottom line, but they're less well known, except probably the first two called Weber and Free Switch, which I will talk about them later. So this is all of those packages, all of those software for the voice IP servers, of course, run on Linux. And the question is Linux voice IP ready? So do we have anything to improve here also? I think that Linux is mostly voice IP ready. So what we need to do basically when you do voice IP only on Linux, of course, any TCP implementation can handle the signaling protocol load. I mean, there are not so much data transferred there. What hurts is UDP. So as I said, in some protocols you can pass data between the endpoints directly, and in some protocols you need to pass data through the server. Or you need to pass data through the server if you need to transcode it, because one of your devices can only talk G711 and another device can only talk SPIX or, for example, G729. And the transcoding takes CPU time. But even if you don't transcode, if you just transfer the data through the server, the payload packets are very small. And you need to process them with the minimum latency, which means that in the ideal case, your application will wake up on each packet to process it and then send it. So this is basically the wake-up storm of some kind. And this is really hurts when you have a large number of clients transferring the UDP data through your voice IP server. There are a couple of ways to solve this problem. The one way is, I mentioned it as a letter, to avoid this problem. So you can design your network not to pass data through your servers, or you can just spread the load across the servers, because you can load balance those servers. It's fairly easy. But if you're really concerned about it and you have 6 months of time, you can probably implement something like the net channels, which is the complete networking stack in userspace. Or we have a similar project here in Google called the Matrix. It's basically the same. You move the networking to user space, and your kernel does only receive the packets and puts it into the memory buffer, which is mapped to your user space application. This reduces the processing overhead of multiple layers in kernel, but this also removes all security, and such kind of stuff. But that's why I mentioned that this is not really useful in general, but can be used here. And so this is with UDP. And another thing that is required for voice IP is just basic things like I said, the CPU scheduler and the high precision timers. But with the new 2.6 kernels, things started to improve here, especially in last 2 months. The CFS scheduler and all this CPU scheduler rewrites. I think this will continue to improve, but the basics are already in place. So I can say that Linux is voice IP ready. So let's go to the PSTN connection. what I want to do is I want to take my Linux box, which is the commodity hardware and which works with voice IP, and I need to connect it to the PSTN to handle the traditional phone calls. So the reasons why I want to do here on this slide is the telephony hardware costs way too much. And the telephony hardware is way less flexible than our software solution. We can do basically anything we want on our software, but some vendor equipment that you buy will just, not allow this. That's all. So you can also easily outperform your vendor equipment on the commodity equipment if you do everything right. Or even if you don't outperform it with a single box, for the same price you can buy 10 boxes and you will still outperform it. And you can also achieve the reliability by connecting, by using the backend connections, Ethernet, and put one E1 interface into each box. And if you want some, 10 connections, you use 10 servers, and each server handles only a small part, only 30 PSTN calls at a time. If one server goes down, you just lose 10% of your calls. So how to connect to PSTN? The ways to connect is, there are personal ways, like analog line plugged into your box, or ESDN basic rate interface, which is the digital telephone, or you can connect the carrier way, so E1 or T1 line with some protocol like ESDN Q931 or SS7, and you also plug into your box. And you have a hardware to do this. Actually, there are some manufacturers which produce the E1 T1 cards. It's the Digium. Digium is the company which basically invented and started Asterisk. And there are Sangoma, the United States manufacturer of the telecommunications card. And there are one Russian company, Chronix, which equipment also can be used in these setups. I actually used it much. So when you connect it, so we actually take the PCI card and plug into your box, and then plug E1 line to your, and the E1 line from some exchange. You plug it to your box. You can do basically what I said before. You can do voice IP PSTN gateway and soft switch with the PSTN access. And you can run everything you just run on your voice IP, any scripts or any your tools on any service. And advanced ways, there are also some advanced usage for this. There are also way to use this as a signaling proxy for PSTN. So sometimes it is required because, for example, you can have a really carrier type Alcatel switch, and the ESDN interface, it can have a lot of SS7 interfaces, but ESDN interface, the single ESDN interface, will cost $10,000. And you can basically buy a card, 2-port card for 1,000 and plug into your box and launch the signaling converter, which will basically, which functions similar to the signaling proxy for the voice IP. It converts only the signaling part, but the voice are the same. It's the same GIS711. You can also do some mobile applications like SMS Center on your box if you have SS7 connectivity, or you can transparently monitor and record calls, or you can collect the statistics from the line as you want. When you connect to PSTN and translate your calls to voice IP and back, you will encounter a couple of problems. One of those problems are echo. The echo is basically, I have some diagrams here. There are two sources of echo: is the hybrid transition and the audio leak. The hybrid transition is the transition which converts the 4 wires, input and output, into 2-wire line which you have at your phone. And when you convert it back, then in your input you will get some reflected signal from output. So basically your signal is echoed back. And this is the first source of echo. And the second source is the audio leak. So your microphone just hear what happens in your earphone. Why you don't notice echo in PSTN? Because in PSTN, in circuit switched network, usually they are very, very low latency. So the granularity of transfer is 1 byte, and they just pass it across all circuits, and everything works. In voice IP, you have chunks of bytes to process, of audio data to process, and you have all overhead of the IP packet transfer, which increase the latency, so you can hear echo here. And there are multiple ways of defeating echo. So echo cancellation and echo suppression. Echo suppression basically is defeating the all conversation. So it just mutes you while other party is talking, and the echo cancellation tries to subtract signal from the. So the other problem with voice IP to PSTN conversion and back is the faxes, which basically faxing over IP network doesn't work. So because of many assumptions which need to be satisfied when you transfer the fax. And there are two types of solutions of this, T37 and T38, which are basically what we're doing. We not pass the faxing audio data through our network. We terminate the faxing on one gateway, and we regenerate it on another gateway. And in T37, it's basically like you have a fax machine, we get the fax completely, and then you send it over the network, and another machine calls other party and tries to send fax there. And T38 is real time. It tries to detect when you turn on your fax, and then switches all the channels, all the gateways to this mode, then transfer the fax in real time, and then switch it back. So what software you need for a PSTN connection? You need the kernel support because you will plug a hardware into your box. So you need a driver for this. And the drivers are usually provided by a joint effort from the Zaptel framework, which is the framework for the telephony, de facto standard framework for the Linux telephony right now. And interface cards drivers. Zaptel includes drivers for DGM hardware, and there are also other manufacturers usually provide the compatibility layer for Zaptel. So as Sangoma and Chronix provides this. And in userspace, you have a library libpri, which used to talk the ISDN Q931 protocol. And you have the software packages itself, which use the libpri, which use the Zaptel, and basically do all the telephony. So the basic instructions to install, it's nothing fancy, just a couple of open source packages, couple of kernel modules which you need to mod probe, and you will have a couple of device nodes in your dev directory, and it will work. Zaptel in-kernel architecture. It's pretty simple, actually. The E1 card driver does nothing fancy. It just generates interrupts when it has data, or it needs to process, or it needs to transfer the data to outside vault. And the line rate is the same. So we regularly get the interrupts, and on each interrupt, we get the data out of the Zaptel framework and put it into the device output buffer. And also we get data from device input buffer and put into the Zaptel framework. All other processing is done, we also call the echo cancellation hooks. All other processing done into Zaptel. So it's actually the huge piece of code, this Zaptel framework, which can do many things that I just mentioned on the right side of the slide. So we can apply HDLC framing to some channels. We need to do this because the ISDN Q931 runs over HDLC. And HDLC requires that we generate the flag bits, and the flag bits need to be generated in kernel because they need to be, the free space in your frame need to be filled with the flags, and it can be generated only on output buffer filling. Zaptel also can cross-connect time slots if your hardware is unable to do this. By cross-connecting, I mean we can pass the calls directly without touching them in software. So if you have two incoming calls and you need to bridge them together, you can do this. In some hardware cards actually can do this, but if you don't, then the Zaptel framework will do this for you. And then it presents the data to user space via device nodes. As I said, you will get a lot of device nodes in your dev directory, and each node will correspond to some channel. So for example, if you have one E1 card, it will have a 31 setup channel. 30 of them will be voice channels and viewer channels, and one of those will be a signaling channel for the SDN-Q31. So we'll have this number of device nodes. And the next question is Linux PSTN ready? It's almost the same question about voice IP, but here I'd like to say that Linux is not PSTN ready. So despite you right now can do this all stuff. You can connect to PSTN, you can do whatever you want. However, the Zaptel framework is external. So it's not actually Linux. You take the Linux kernel, and if you want to do something with this, you need to deal with external model. And the external models are usually, the problem with external models that they have a lot of compatibility stuff inside because they intended to run with the different versions of kernel. And basically it's a big mess to try to handle this. And each kernel versions change the interfaces slightly, and you need to forward the Zaptel to it. And it also contains lots of stuff which I don't understand why it is there. For example, it contains the timing source. Some time ago, Linux 2.4 timers were not so reliable, and basically what Digium decided in their asterisk, they need the timer. And we know that our interface card, our E1 interface, anyway generates the interrupt for each data transmission. So we use this interrupt as the timing source. And we have a special code in the driver which interprets this and also allows our user space application to be driven for these events. And the Zaptel, for some reason, contains the whole conferencing API, so the whole audio mixing code in kernel. So you don't do any mixing in user space, you just open the device node and then feed audio to this device node, and kernel does all mixing. It's not easily readable, so it's a perfect example of copy and paste programming. And many features are done wrong. And there are also some performance and scalability concerns. So right now, every channel uses its own device node for data transfer, which means if you have 4 E1 interfaces, you will have 120 device nodes to read audio from. And if they are all talking to someone, then you will need to basically you will need to do 120 different reads at each interrupt, so 1,000 times per second. And this can be easily fixed by coupling, but it requires the rewrite of the Zaptel framework, of course, but this can be fixed by merging the B channels together because they all belong to the same card, to the same interrupt. You can read them at one pass. There are also echo cancellation, which can double the load, and echo cancellation right now is done in the interrupt context by Zaptel. So you can also fix this. I think if we move this to user space, we will be allowed to distribute it across the CPU cores. And this can be offloaded to hardware, but dedicated echo canceller for 30 channels costs at least twice as much as the new CPU. And new CPU can obviously handle not only echo cancellation. So there are short history course into the Linux telephony. So as I said, the Linux-based telephony started to gain popularity with *1, which was in 2004. Somebody already used the asterisk before the release, but the buzz started in 2004. And we have a new hardware player since then, right now in 2007. And we have a new software packages. And we have some software which was before asterisk, but largely forgotten. And this slide probably isn't so readable at all. So in modern history, what we have a call weaver, which is the fork of the *1.2. The fork is more open because in asterisk, Digium requires you to disclaim the copyrights. And some features, for example, the generic timer support instead of the timer, the Zaptel timers, which I was talking about, was never merged to asterisk, but was merged to CallWeaver. And right now, CallWeaver is much more portable than asterisk, so it can run on FreeBSD or on macOS or whatever. And it contains the most working the T38 implementation, so faxing support. There are also many internal improvements, like replacing the linked list of all numbers with the hash table. You know what I mean? It's in asterisk on each action you traverse the linked list of all numbers in your dial plan. The free switch package, which is the relatively new, it's the different architecture started from scratch by a guy who once hacked on asterisk, but then decided to write his own voice IP package. And basically, it doesn't contain any PSTN support, but for soft switch, it's already feature complete. And there are 8, which is, as I said, is the very high performance engine and can use a native WAN pipe interface to Sangoma cards because it is partly sponsored by Sangoma. But it also does some stuff better than asterisk. So do you have any questions about what I talked so far? No questions?
You mentioned this they are all open source free software, right?
Yes.
So what about those commercial ones?
But the commercial one. The problem is that the commercial software for the voice IP and for the PSTN connection, especially for the PSTN connection, usually comes with some hardware part. You know what I mean? So if you want to connect to PSTN to process the calls, they used some vendor equipment, which is so it's effectively a bundle, and this is not Linux based. This will not. It can be Windows or some proprietary OS. So this is essentially outside the scope of the Linux telephony presentation. So I don't know what else to say to answer on this question. Any other questions on the technical part or?
What's the current state of SS7 support with asterisk? You mentioned that it's there. Is it free? Is it how stable is it? Is it being used much?
There are three, as far as I know, three implementations of SS7 protocol for asterisk. One of those are commercial, and two of those are free. The two free implementation, actually one of those is working. I tried it on SS7 equipment and it works. It's the Zephyr AG SS7, Chen SS7. The problem with SS7 is it's not so easy to get a point code, which is the address in SS7 network, if you don't run certified equipment. And the equipment is certified as a whole. So right now, SS7, open source SS7 can be useful only for people who work in carrier or who work in some company which manufactures the equipment. So I worked in the cell phone carrier. So this was very useful for me, and I did many things using it.
Nobody wants to talk SS7 to the average Joe.
I don't know. There are some. Probably they're afraid of, some not certified software will nuke the whole network down. Something like this. So a couple of success stories that I have also during the couple of years. This is all possible with the current state, with the current software and the current kernel. However, as I said, I'm not very satisfied with the PSTN support and it needs to be redone, but on the other hand, this is all possible. And for example, with the load testing of vendor voice IP equipment, I was almost every time able to outperform very expensive equipment of some vendors. For example, the Alcatel, or probably I tried Norton. Yes. So this is probably last slide. Excuse me? Can you repeat the question?
So, how do you do, I missed the first part, so I'm going to miss this. How does name resolution happen? So how do I register a phone number and be able to plug into somebody's public Wi-Fi and actually get a call? Is there anything like that going on to sort of create a namespace for customer ID?
There are actually a couple of problems here. The first problem is that in PSTN, in traditional phone network, we require that all numbers are essentially routable, so it's the global routable addresses. When you try to use some random voice IP network, for example, random SIP network, it doesn't imply anything at all. So you connect to this network, but you don't get any number or any global address automatically. Some networks, however, try to interoperate. And there are some ways to do this. And also some networks try to interoperate with the traditional networks. But the basic idea is that we have a voice IP gateway somewhere which takes the calls from the PSTN and forwards them to your phone number. But this is, right now, this is largely handled on the individual basis. In some open source implementations, for example, in Asterisk can support this and Weaver can support this. There's so-called DNS E164 support, which means that if you register, if you have a voice IP gateway and you want to make it public, you can register it in DNS with the special name. And then if someone who supports this standard also will try to call some PSTN number from his IP phone, it will locate this gateway and try to terminate the voice IP call into PSTN network on this gateway. But this is all that is done so far with the routing and with the interoperation. And there are also another possibilities. For example, there are a couple of voice IP exchange, some kind of, I don't know, some organizations which basically trade the voice IP traffic. And if you use some, for example, if you use the Cricket to call the PSTN number, then I actually tried to call some numbers in Russia and then traced it. We use some voice IP gateways, which is operated by some voice IP providers which charge for this. So there are some central exchanges when you can just put some money in and they will give you some amount of minutes on a different, in the different regions. So something like this. But so basically it's all. Any other questions? I was mostly interested, I was somehow interested in some technical questions because the issues that we have with kernel support of the voice IP, of the PSTN, require a significant redesign of the Zaptel framework. Or, I'll better say, we need to write a new telephony framework. And I wanted to ask if somebody wants to volunteer to do this. This is essentially the Linux kernel stuff. The simple framework and the I don't hear. So, but you know, I've got almost no technical questions, so obviously I failed with my expectations. So anyway, thank you all for listening to me. I hope that you found some interesting bits in this presentation. And if you're interested, you can do two things. You can go to the voice IP wiki, which is the voice IP info.org, and you can contact me directly. I'll try to explain something which left dark here, or if I screwed up some explanations, you can just ask me another time. So if you don't have any other questions, thank you.